This video covers Part 1 of Section 1.3, Logical Implication. Suppose P and Q are two compound statement forms. If the conditional statement form P implies Q is a tautology, then we call P implies Q an implication. And we say P logically implies Q. In this case, whatever P is true, then Q must also be true. So the truth of P forces Q to be true. We say that P is a stronger statement than Q, or that Q is weaker than P. For our first example, let's show that the conditional statement forms P and Q implies P, and P implies P or Q are both tautologies, and hence P and Q is stronger than P, and P is stronger than P or Q. And then we want to look at what can be concluded from these implications. To show that these statement forms are tautologies, we can just construct their truth tables. So we'll set up the tables as shown and fill in the tables a column at a time. Since both statement forms are true for all possible choices of truth values of their statement variables, both are tautologies and hence implications. Since P and Q implies P is an implication, then P and Q is stronger than P. This means that whenever P and Q is true, then P must be true. Similarly, since P implies P or Q is an implication, then P is stronger than P or Q. So whenever P is true, then P or Q must be true. Both of these conclusions follow immediately from the conditions under which P and Q is true, or P or Q is true, so we didn't really need to verify the two implications to draw these conclusions. For another example, we want to show that the quantity P implies Q and P implies Q is an implication. To show the statement form is an implication, we can construct its truth table and verify that it's a tautology. Since it's true for all choices of truth values of P and Q, the statement form is a tautology and hence is an implication. This implication is called modus ponens, which is Latin for method of affirming. This is one of the most widely applied implications both in and out of mathematics. In mathematics, many theorems have the form of a conditional, P implies Q. Suppose we wish to prove that the conclusion of the theorem, Q, is true. Since we know that the theorem P implies Q is true, if we show that the hypothesis of the theorem P is true, it then follows that the hypothesis P implies Q and P in modus ponens is true. And since this is an implication, we can then conclude that the conclusion Q must be true. For instance, suppose we know or have proved the theorem, if the ones digit of an integer is 0, then the integer is divisible by 10. Suppose we then have an integer, say 7,540, whose ones digit is 0. We can then conclude using the theorem and modus ponens that the integer 7,540 is itself divisible by 10. We actually use this line of reasoning all the time without thinking of each of the steps involved. The following theorem lists some of the more important implications. As for theorem 1.2.2, each part can be proved by constructing a truth table. So the theorem starts with the following statement forms are all tautologies and hence implications. The first is the law of simplification, the law of addition, the law of disjunction, modus ponens, and modus tollens, which is equivalent to a proof by contrapositive. The next group, we have the law of syllogism for biconditionals, and proof by contradiction, vacuous proof, and the trivial proof. And the biconditional implies the conditional. Note that when P and Q are logically equivalent, then P if and only if Q is a tautology. This means that both P implies Q and Q implies P are tautologies, so P logically implies Q and Q logically implies P. So each of the equivalences in theorem 1.2.2 in the previous section also yields two implications. For our next example, let's verify that the law of syllogism, P implies Q and Q implies R, quantity implies P implies R, is an implication. And then we want to look at what can we conclude from this implication. To show the statement form is an implication, we could construct its truth table. Alternatively, we could reason as follows. Since the statement form is a conditional, the only way it can be false is if its hypothesis is true, but its conclusion is false. That is, P implies Q and Q implies R is true, and P implies R is false. The hypothesis P implies Q and Q implies R is true if and only if P implies Q is true and Q implies R is true. The conclusion P implies R is false if and only if P is true and R is false. Then P implies Q is true and P is true hold if and only if Q is true. So in order for the statement form to be false, we must have Q is true and R is false, which imply that Q implies R is true implies false, which is false. Not true, as we said we needed above. This shows that there is no way the original statement form can be false, meaning that it must always be true. So we cannot satisfy the conditions for the statement form to be false, so it must always be true. Therefore, the statement form is a tautology and hence an implication. Now this procedure is sometimes going to be a little bit easier and quicker than constructing a truth table. Other times a truth table might be the most straightforward way of verifying that this is an implication. Now what can we conclude from this implication? Since this statement form is an implication, whenever the hypothesis P implies Q and Q implies R is true, then the conclusion P implies R must be true. That is, if we know that P implies Q and Q implies R are both true, then P implies R must also be true. Suppose we know or have proved the theorems. If the ones digit of an integer is 0, then the integer is divisible by 10. And if an integer is divisible by 10, then it is also divisible by 5. What theorem can we conclude from these two theorems using the law of syllogism? First, define the statement variables. P is the ones digit of an integer is 0. Q is the integer is divisible by 10. R is the integer is divisible by 5. The two theorems then have symbolic forms, P implies Q and Q implies R. Assuming both of these theorems are true, then the hypothesis, P implies Q and Q implies R, in the law of syllogism is true. And since the law of syllogism is an implication, we can then conclude that its conclusion, P implies R, is true, which corresponds to the theorem, if the ones digit of an integer is 0, then the integer is divisible by 5. Next, we want to verify that not P implies Q and not Q, quantity implies P, is an implication. To show this statement form is an implication, we can construct its truth table and verify that it's a tautology. So we'll set up the table as shown and fill it in a column at a time. And since this is true for all choices of truth values of P and Q, the statement form is a tautology and hence is an implication. This is referred to as the proof by contradiction implication in the theorem. So this implication is the basis for a proof by contradiction. Note that the conclusion of the first conditional in this statement, Q and not Q, is always false and hence is a contradiction. Suppose we wish to prove that the statement P is true. If we can prove that not P implies the contradiction, Q and not Q, then the implication enables us to conclude that P is true. So basically what we're doing is we're proving the hypothesis of this conditional is true, and since this is an implication, we're able to conclude that the conclusion P must be true.